And thank you for this nice opportunity. Today I'd like to introduce the recent updates of the library kokkos-fft. And this is the team effort of the SEGSA team from CEA. So firstly, why kokkos-fft and who needs it? So this is for someone using Kokkos to report a legacy application which relies on fft libraries, like free simulation cores with periodic boundaries or plasma turbulence. Another example is having a Kokkos code and waiting to integrate their in-situ and data processing with FFTs, like spectral analysis or low-pass filter or whatever. And also who is not waiting to get through the documentation of the facto standard libraries, because these FFT libraries are shown in the right bottom, and these have their different APIs for some reason. So the key idea is that in the we'd like to still benefit from the powerful FFT libraries by vendors, but still make it as simple as something like numpy.fft, because this is one of the most simplest one. In kokkos-fft, the basic APIs follow the numpy version, but slightly different, but because of the execution space and the return value is also an input argument. And actually, we also need this library because we are developing the X++ code for plasma turbulence, which is periodic along toroidal direction intrinsically. So we can use this library. And this slide summarizes the key features of kokkos-fft. And this is as simple as NumPy, but as first as vendor libraries. It's supporting the 1D to 3D standard and real transforms, 1D to 8D Kokkos views, and batched plans are automatically used if view dimension is larger than the FFT dimension. The simple interface like NumPy supporting the auto-place and in-place transforms, and view is all we need. No need to access the complicated FFT APIs, and much safer APIs, and no need to use raw pointers directly. And there are compile time or runtime errors for embedded usage. We are supporting the serial thread and OpenMP, CUDA, HIP, and SQL backends for the moment. And the FFT libraries dedicated to Kokkos backends are automatically enabled. The supported data types are the float and double for the complex also, and limited to contiguous data layout, meaning layout left or layout right. And default execution space and default host execution space are recommended. The APIs, as I said, it's for the numpy.fft, and basically we have the kokkos-fft func, which is equivalent to the numpy.fft.func. A namespace starting from the kokkos-fft APIs, and implementation details are under impl namespace. There are some macros starting from kokkos-fft. In this example, and the real-to complex transform is made, and for the 3D data in the batched plan. And this is a Python version, and corresponding Kokkos version is quite simple and almost identical. More like the random initialization is more costly. In implementations, and we may perform the transpose depending on the choice of the axis you would like to perform FFT, and then create a FFT plan and execute FFT followed by normalization. And for invalid usage, we will make an error. Can be compile time error if execution space is not accessible for views. And the FFT plans can be reused. This is important for cufft or rocfft, where the plan creation cost is non-negligible. And this is the usable plan APIs, where we can use the plan for different data. This is the example for the 2D case, and the creator plan for this 2D data on the X. Of course, you can execute TFFT on the X and X hat, but you can still use this plan for the Y and Y hat because these are the same extents. However, you cannot run the FFT on the Z and Z hat because the extents are not identical. You will have the runtime error in this case. And these plans can be used multiple times, so it's recommended to make these plans in the initialization stage and reuse it repeatedly. And the in-place FFT plan can be also reused, but it's limited to in-place transform. You cannot use in-place FFT plan for the out-place transform because they are not identical. This example shows how this library makes this realistic usage simple. The right front, this is the example of the solving the two-dimensional and the plasma turbulence simulation, solving a convolution with fft. And the right example is coming from NumPy, which is highly readable and much more simpler compared to the Kokkos version. The corresponding Kokkos version is a little more complicated because we made some optimization. We have some optimization, and making a single view and having all the derivative value, and just use the sub-view to that to have performed the convolution in this case. So it's a little more optimized. As you may imagine, if you achieve the same code in NumPy and the Kokkos, you will expect a significant increase of lines of code and complexity. Of course, NumPy version is simpler, but the Kokkos version is just in the 1.5 times longer than that. The benefit is clear because we can run anywhere, like NVIDIA GPUs and AMD GPUs and Intel GPUs with the same code. And the benefit is big because the elapsed time compared to the Python serial version, you may sometimes observe more than 3,000 times faster. And this animation shows in the same time scale and how their simulation progresses on different architecture. And at the 800 simulation is soon into their turbulent state, and 800 and follows that, and they might have 250x follows that. The Python and Ice Strike is almost stalled, but it's still progressing very gradually and very slowly. This is a build system, and we depend on the CMake, and basically supports the same compiler version for the Kokkos backend. And the some key feature is that if you enable the fftw on even for the device backend, you can use fft for host and device using the fftw on host and cufft on device, for example. So, and this may be useful for the initialization, for example. And the easiest usage is to use kokkos-fft as a subdirectory, and your project looks like this. And you have CMake and Hello and your TPLS and Kokkos and kokkos-fft, and CMake list can be something like this. It's quite straightforward, and you can just use the Kokkos compilation command to enable kokkos-fft, and basically that's it. So it's quite easy to use. And CI in CD is basically made on the GitHub actions and relying on Docker and Singularity. And our build system in the format test and license check and the crank format and crank tidies are made. And for the build test and the install tests are made on each backend in the container on the GitHub actions. As for the run test, and we will make the serial and CPU backend test on the GitHub Azure. But for CUDA, we will run our internal server and using self-hosted runner. Hip and SQL are not run test is not made for hip and SQL. And documentations are auto-generated against the main branch and hosted on the Lisa docs. And this is how the documentation looks like. But briefly, all the APIs are auto-generated from the doc strings of the C++ code in order to keep the consistency. And using the brief, and these APIs are generated APIs from Doxygen are embedded into the Sphinx, and so you have something like this. And there are some contents including developer guide. And the coming features of targeting Kokkos 5.0 is the unit testing tools, which may be used for other Kokkos ecosystem potentially. And we are currently developing the view-to-view matcher on device, which allows us to compare the two different Kokkos views on device in quite performant and quite easy way. And another one is the distributed FFTs, which may be used by somebody. So we are currently developing it, and it is actually the collaboration with this internal collaboration with Kokkos.com, and to perform their more performant version like Nico or Roku backend. But this is currently under development. And the summary, the features are just easy to use, and there are some sort of modern CI and CD and documentation. The future plan for release 1.0 includes this pack recipe and the multi-GPU support and batch capabilities under consideration. And also unit testing tools are proposed. And so that's it. And you can find it in the under Kokkos org. And thank you for listening. Thank you for listening.
Okay, thanks. While Matt is setting up, we have time for 1 or 2 questions, depending on how long he will take. Yes.
That's maybe more a comment. So for your distributed FFT, are you planning to look into hftw? I mean, that was an ECP project that basically did distributed performance portable FFTs. Are you planning to look into hftw?
Yeah, I didn't explain explicitly, but the collaboration with Oak Ridge stands for the collaboration with hipfft. So yeah, of course, and we have made it. And so we may probably do something quite similar, but there are some experimental approach, like using the kokkos-conf for the communication backend, which may sometimes accelerate some communication patterns.